Hi, I'm Michael Baddeley, and this is 6TiSCH++ with Bluetooth 5 and concurrent transmissions. This is a joint effort between the University of Bristol, Graz University of Technology in Austria, and Toshiba Europe, also in Bristol. Since submitting this paper, I've actually moved on, and I'm now working for the Technology Innovation Institute here in Abu Dhabi in the UAE. So I'm going to assume that the majority of the attendees here at EWSN will have at some point heard of 6TiSCH and how this relates to low power wireless networks. And if you've ever been to this conference before, I'm sure you've heard of concurrent transmissions, also known as synchronous transmissions, and how these can actually enable a very highly reliable, low latency flooding technique called synchronous flooding. And I'll give a very brief background on both of these just to bring everybody up to speed. We'll then look at modern wireless chipsets, in particular single radio multi-protocol SoCs that allow you to switch between multiple different physical layers with very little overhead. We'll then look at how both of these points actually relate to 6TiSCH++ and how we use this multi-PHY and multi-MAC technique in order to address some of the weaknesses within the standard. We'll then look at what this paper itself achieved and what is still to be done, what's next. So in a nutshell, 6TiSCH defines mechanisms to create and disseminate scheduling information for the time-slotted channel hopping or TISCH MAC layer introduced as part of IEEE 802.15.4 in the 2015 amendment. And this really allows you to do things like schedule orthogonal transmissions across co-located nodes and design optimal routing and scheduling paths across the network. And the standard defines two main approaches to actually creating these schedules. The first is distributed, and the second is centralized. In the distributed scheduling approach, nodes will communicate amongst themselves and the neighbors to define an optimal local schedule, but this is done without a view of what's going on in the rest of the network. In the centralized approach, nodes will go over multiple hops to ask a root node or a controller to come up with an optimal solution for them, and this root node or this controller is able to do this with a global visible view of what's happening within the network itself. What this means is that the distributed approach is more scalable but has less visibility, whereas the centralized approach has greater visibility but is less scalable. And this brings us nicely to concurrent transmissions and synchronous flooding. Now, usually when two nodes transmit at the same time, they cause destructive interference and actually collide at the receiver, meaning both transmissions fail. And this is the entire point of 6TiSCH and of time-slotted channel hopping, is that by scheduling communications optimally across the mesh network, you're able to actually have multiple nodes transmitting simultaneously because they're transmitting on orthogonal frequencies. Now, concurrent transmissions actually solve this issue of how to have multiple nodes transmitting on the same frequency at the same time. And it does this using two physical layer properties that are present in FSK modulated systems. The first property is non-destructive interference, which allows nodes to actually simultaneously send the same data as long as they're well synchronized. And this is to within half a chip period. So for example, in IEEE 802.15.4, this is about 0.5 microseconds. The second property is the capture effect, where if one transmission is received with significant power above another transmission, then the higher power transmission will actually be reliably demodulated. And this allows nodes to compete in order to send different data. So the fact that concurrent transmissions don't collide and don't suffer from this contention problem means that we can use this technique to build up very highly reliable and very low latency synchronous flooding protocols. Now these protocols, they work in a number of different ways. There's quite a few out there, but generally what happens is that nodes will synchronize to an initiator. They'll then sleep because they know the next flooding period. Just before the next flooding period, they'll wake up and they'll begin to hop channel depending on some pseudo-random channel hopping pattern. They'll then receive a transmission from an initiating node, and they'll immediately begin to transmit. And because they don't care about contention, they don't need to negotiate any sort of transmission schedule with their neighbors. So hopefully that's given you a bit of background into 6TiSCH and how concurrent transmissions can support these ultra high reliability, low latency synchronous flooding protocols. Now, one of the chipsets that's been very popular in concurrent transmission research over the past couple of years has been the NRF 52840. Now, this is actually a single radio multi-protocol SoC that can support multiple 2.4 gigahertz physical layers. In particular, it can support all the 4 BLE physical layers, plus also the IEEE 802.15.4 OQBSK DSSS physical layer that is typically targeted by the IETF 6TiSCH standard. Now, this is important, the fact that it can support these multiple physical layers, because it can do this with only 40 microseconds of overhead. Essentially, it's just the time that's taken for the radio to ramp up. But why do we care about this? Now, we care about this because the different physical layers can help support CT-based flooding in different ways. For example, the higher data rate physical layers, such as the BLE 2 megabit per second, physical layer can support over-the-air firmware updates. Additionally, the BLE 500K and the 802.15.4 physical layers have been shown recently that they really help support concurrent transmissions under interference. And if the nodes are well synchronized and actually follow a known schedule, then there's very little overhead to switch in this physical layer depending on the current network situation or your current use case. And all it takes is this 40 microseconds in between each flood in order to be able to do this. And this is really the key thing that the 6TiSCH++ approach is targeting. Is firstly looking at the MAC layer and trying to address weaknesses within the standard by leveraging the strengths of your concurrent transmission-based synchronous flooding. So this is really looking at synchronization of the entire mesh network, fast association of the nodes within the network, and also establishing downward routes to allow you to update scheduling information or send acknowledgements from a centralized controller. And then secondly, using these modern wireless chipsets in order to take advantage of these multiple physical layers and actually switch the physical layer at runtime to tailor your concurrent transmissions based on your network conditions. As I said in the previous slide, this can give you high data rates, it can give you long range, or it can give you increased reliability. And we find that CT-based flooding protocols are actually rather amenable to the 6TiSCH standard. You know, synchronous flooding protocols are by nature highly synchronous and deterministic, but more importantly, they're actually bounded in time, so you know exactly when they're going to end, which allows you to fit this flooding concept quite neatly within the TiSCH slot frame structure. Not only that, but 6TiSCH itself actually defines the concept of mutable hard cells as well as negotiable soft cells, which allows you to set up flooding periods within the TiSCH slot frame itself. And importantly, when we're talking about these modern low-power wireless chipsets that allow you to have multiple physical layers on a single radio and switch between them at runtime with very little overhead, we can actually set up the concurrent transmission protocols to run over the various BLE physical layers or even the 15.4 physical layer, but it gives us these options. It allows us to do high data rates, allows us to do long range, or allows us to switch the physical layer in order to better combat interference. And then we can actually then switch the radio back to 15.4 and run the 6TiSCH slot frame as normal. So in 6TiSCH++, we really set out to see if we could use this concept of changing the physical layer at runtime in order to support both Bluetooth-based concurrent transmission flooding as well as the standard 6TiSCH IEEE 802.15.4 physical layer and switch between these at runtime. And specifically, within this paper, we use 6TiSCH minimal in order to reserve hard cells depending on the length of the concurrent transmission flood. But this could really be any sort of scheduling protocol, as long as you make sure that you reserve this period of time in which the concurrent transmission-based flood can actually happen. We then also periodically broadcast the 6TiSCH enhanced beacons through the CT flooding mechanism, which provides network-wide highly accurate synchronization and actually removes the need for keep alive messaging within the standard. And then finally, we also use a technique that's previously been demonstrated in a paper called Root or Flood, where you send the ripple DAO axe also through the CT flooding mechanism that allows you to significantly reduce the signaling overhead involved in establishing downwards ripple routing through the mesh network. So if you now have this ability to switch the MAC layer and the physical layer at runtime, so we can switch from the standard 6TiSCH protocol to being able to do a network-wide broadcast using concurrent transmission-based flooding, and also do this at, for example, higher data rates using the Bluetooth 5 physical layers, then we can see that this opens up a whole new set of use cases where we can do high data rate transmissions, for example, for over-the-air firmware updates, and we can do this over a further number of hops within the same amount of time that we can only send maybe 1 or 2 messages using standard 6TiSCH scheduling techniques. Furthermore, we decided to evaluate this on DCube, which is a mesh benchmarking testbed based in TU Graz in Austria. And many of you may remember DCube from the dependability competition that's been run during previous editions of EWSN, although unfortunately it wasn't last year. So DCube hardware is essentially an adapter that allows unobtrusive testing and jamming of mesh protocols. And importantly, it actually manages the sending and receiving of messages across the testbed in an automatic and repeatable fashion, and collects metrics on power, latency, and reliability of those messages, which is then able to automatically analyze in the backend system. Now, although DCube isn't the only testbed out there, importantly, it has this unique feature of a 2.4 gigahertz jammer on each and every single node, which allows you to measure the performance of your solutions under interference. So using the DCube testbed, we wanted to first of all look at two key things that 6TiSCH++ does. The first being that it sends out these enhanced beacons using the CT-based flooding protocols, and the second being that it uses the same mechanism to send out the ripple DAO axe. Now, in the first instance, we were looking at the time taken for all nodes to associate to the network. And we can see that 6TiSCH++ is able to actually synchronize all the nodes within the network within a fraction of the time that the standard 6TiSCH solutions do. Secondly, we're looking at the time taken for all nodes to establish a downwards ripple route back to the nodes within the mesh network. And we see that although maybe not quite as significant a difference as in the first cases within synchronization and association to the network, we still massively improve on the standard 6TiSCH protocols. So the key thing that 6TiSCH++ really focuses on is replacing the mechanisms for sending out messages from the root node with sending these messages out over the concurrent transmission flooding period. And what this gives you is a mechanism that's very, very reliable, very low latency, and actually means that you don't need to have quite as many retransmissions and negotiations and control signaling in the rest of the network. What this does is that this opens up the rest of the slot frame, which is no longer needing to deal with control signaling, to focus purely on the layer 3 application traffic. So we ran tests in DCube to see how would this actually affect the latency and the reliability of your regular application traffic. And what we find is that because of this reduction in control signaling, 6TiSCH++ is able to achieve significantly lower latencies, both with and without interference, as well as maintaining this very, very high reliability that 6TiSCH is known for. So what next? Well, this paper has explored how to use Bluetooth 5-based concurrent transmissions, of which there's been significant interest in over the past couple of years, particularly from this conference, to address weaknesses within the 6TiSCH standard. And specifically, we're leveraging the power of the single radio multi-protocol low-power wireless chipsets in order to provide fast and highly reliable synchronization mechanisms for the 6TiSCH network. And this could help, for example, to open up the standard to mobility use cases, something that is really not focused on at the moment, and also to help reduce the generous guard times that provisioned within each slot and indeed, lower the latencies that are possible within the 6TiSCH standard itself. Secondly, we've shown that it's possible to provide really reliable, low latency centralized control signaling, which frees up the rest of the slot frame for layer 3 application traffic, and also helps to support the concepts of software-defined networking, which are part of the 6TiSCH standard, but which have really never been realized. And then finally, it's shown the viability of actually switching this physical layer at runtime on a single radio. And as mentioned previously, one of the big interest from Toshiba in this was, the fact that we could support over-the-air updates. But it really opens up the research space to things such as adaptive control protocols, whereby you're able to actually switch the physical layer at runtime in reaction to the current network conditions, or maybe even to support different application traffic. Thank you so much for listening. I hope you enjoyed both the presentation and the paper. I think I mentioned in the first slide that I've actually now moved on from Toshiba, so if you do have any questions, feel free to contact me at this address, and I hope you enjoy the rest of the conference.